you've mentioned this thing where if you understand the program deeply, you might be able to say something. So can we say something interesting about maybe statistically, how many programs we know something about in terms of whether they halt or not, or what does it mean to understand a program deeply enough to be able
Right.
to make a prediction?
The main lesson of computability theory, in my view, is that it's never the case that you can have a thorough understanding of the behavior of a program by looking at the program, and that the content of what you learn from a program, I mean, in the most general case, is always obtained just by running it and looking at the behavior. And the proof of that is there's a theorem called Rice's theorem, which makes that idea completely robust. But I want to just take a little detour towards another question, riffing on something that you just said. Namely, one can ask the question, uh, what is the behavior of a random program? So you have some formal computing language, and you want to, look at the collection of all programs of a certain size. Maybe there's only finitely many. And can you say something about the behavior of a randomly chosen one, like with a certain likelihood it will have a certain behavior? And the answer turns out to be extremely interesting. Once, years ago, Alexei Myasnikov asked me a question. He had this concept of a decision problem with a black hole. And what that means is it's a decision problem, which is possibly difficult in the worst case, but the difficulty was concentrated in a very tiny region called the black hole. And outside of that black hole, it was very easy.
Mhm.
And so, for example, this kind of problem is a terrible problem to use if you're basing your encryption scheme. You don't want to use a black hole problem, because if someone can rob the bank 95% of the time, then that's not what you want, or even any non-trivial percent of the time is too dangerous. So you don't want to use problems that are, almost every case is easily solved as the basis of your encryption. And the question Alexei asked me was, does the halting problem have a black hole? And so if we take, say, the standard model of Turing machines, it's one-way infinite tape with zeros and ones on the tape, and so on, the head moving back and forth, and, it stops when it gets into the halt state. Then it turns out we proved that there is a black hole. And what that means is there's a computer procedure that decides correctly almost every instance of the halting problem. Even though the halting problem is not decidable, we can decide almost every instance. So more precisely, there's a collection of Turing machine programs such that we can easily decide whether a program's in that collection or not. And for the programs in the collection, we can decide the halting problem for those programs easily. And furthermore, almost every program is in the collection, in the sense that as the number of states becomes large, the proportion of programs in the collection goes to 100%. So the asymptotic density of the programs is 1.
Mhm.
And the proof was quite fascinating because it's one of these situations where the theorem sounds really surprising, I think, to many people when I first tell it. I mean, to computability experts, then it's sort of intriguing to think that you can solve almost every instance of a halting problem. But then when they hear the proof, it's completely a letdown. Unfortunately, nobody likes the theorem after the proof.
Mhm.
And so the proof is so simple, though. If you know how a Turing machine operates, there's this infinite paper tape on which the machine writes zeros and ones, and the head moves back and forth according to rigid instructions. And the instructions are all of the form, if the machine is in such and such a state and it's reading such and such symbol on the tape, then it should write this symbol on the tape, and it should change to this new state specified, and it should either move left or right as specified. So a program consists of instructions like that. If you look at a program, one of the states is the halt state, and that's when the program halts. But you can calculate how many programs don't have any instruction that transitions to the halt state. You can easily calculate the proportion. And in the limit, it goes to 1 over e squared, 13.5%, if you calculate the limit. the proportion of programs with end states that don't ever halt because they don't have any instruction saying halt.
Mm-hmm.
Those programs obviously never halt because they can't halt. They don't have any instruction that says halt.
So 13% of programs, you could
13%
say,
you can say they don't halt because you just look at them and you can
there's no
understand
halt
them.
state.
They never change to the halt state, so they can't halt.
I mean, that nevertheless is beautiful to know,
Yeah.
to show.
So that's a kind of trivial reason for non-halting. And when I first made that observation, I thought, okay, this is the proof strategy, because I wanted to say at first, the goal was, look, that's a stupid reason for a program not to halt. And I just want to pile up as many stupid reasons as I
Yeah.
can think of until it gets more than 50%. And then I can say most. Yeah.
Yeah.
Yeah. That
No,
was
it's
my
brilliant.
goal.
I love this.
Yeah. So
Uh-huh.
we thought more about it, though. And we hit the jackpot because we found one gigantic stupid reason that converged to 100%. I mean, in the limit. And so, and the stupid reason for a program not to halt is that, well, if you think about the behavior, say the head is sitting there, it's on the leftmost cell of the tape at the very beginning. It's in the start state. And the head is following an instruction, and the instruction says, when you're in the start state, which it is, and you're reading something on the tape, then you should write something and you should change to a new state, and you should either move left or right. But half of them move left. But if you move left and you are already at the end, then the head falls off. And so the computation stops because the head fell off the tape. That's a pretty stupid reason. Okay, but that's half of them already, just like that. Okay, and then some of them went right and they changed to a new state. And amongst those, the new state, half of those ones are going left and half are going right from that place. And then most of those are changing to a new state. When there's a lot of states, it's very likely that the next state that you transition to is new. And so you get this random walk behavior, if you know what that means, where half go left and half go right at each step. And there's a theorem due to Polya, which is called the Polya recurrence theorem, which says when you have a random walk, a one-dimensional random walk, then it's very likely to come back to where you started. And when that happens for us, then half of them from that place fall off on the next step. And so you can show, using this kind of analysis, that the probability one behavior of a random Turing machine is that the head falls off the tape before it repeats a state. And that is the stupid proof that shows how to solve the halting problem. Because when that happens, we can answer the halting problem saying, no, the computation stopped because the machine crashed, not because it halted. So therefore, it doesn't count as halting on some accounts. Or, if you want to define that as halting, crashing as halting, then. But in any case, however it is that you set up your formalism, you're going to be able to answer the question for the behavior of the machine when the head falls off.
So statistically, in the limit, you solve the halting problem.
Yes, exactly. Computably solve it, yeah.
What do we take from that? Because you didn't solve the halting problem.
No, it's impossible to fully solve
Right.
the halting problem correctly in all cases.
That's pretty cool. That's kind of, I don't know.
It's a probabilistic way. I mean, it's probabilistic in the sense that we're solving almost all instances computably. There's versions of this that are maybe more interesting from the point of view of complexity theory and actually useful. I mean, there's the whole P-NP problem and so on, and there's this genre of NP-complete problems, which are problems that are infeasible. They would take exponential time to solve them in the ordinary way, and they're not known to be polynomial time solvable, although in these cases it's an open question whether there is a polynomial time algorithm, a feasible algorithm. And for most of the NP-complete problems, you can prove that there's a polynomial time approximation that solves almost all instances in a feasible amount of time. So like the knapsack problem, packing problems and so on, other kinds of problems, satisfaction problem, when depending on how you set up the formalism, you can prove, and I've proven many instances of this, but also I think it's widespread, for almost all the NP-complete problems, the difficult problems, and these are important problems for industrial application, and these are problems that we actually want to solve, we can have feasible algorithms that solve almost every instances of them.